In Chapter 5, we'll be computing the GC content, which will have us looking at FASTA files and analyzing sequences that are represented like that. So far we've just seen the the sequences printed just one on a line, and now we're going to be looking at a new file format. So if we look at the Rosalind GC page, we get an idea of the problem and what the data set is going to look like. So FASTA format comes from a program written many years ago by Bill Pearson called FASTA, which came from FASP. And in that, a sequence identifier starts with a greater than sign at the beginning of the line, followed by some sort of a sequence ID. And modern FASTA files can have a space here and then a bunch of other information, but we're not going to worry about that. We're just going to have a sequence ID here. It should be unique. And that will be followed by one or more lines of DNA sequence. And the output from this sample set should be the ID of the record that has the highest percentage of bases that are either G or C. And I have a few notes about why we care about GC. For instance, the DNA sequences that encode proteins tend to be found in GC-rich regions. So there could be a lot of reasons for wanting to filter sequences based on GC content, and so it's just one of those things that we typically want to know, and it's a fun exercise to learn a bunch of new things here, especially about how to parse FASTA files. And to do that, we're going to be bringing in the Bio.SeqIO. I do know that a lot of people like to start off by teaching beginners how to parse FASTA manually. I just don't see any value in that at the moment. I think it's more important to jump right ahead to using the FASTA format, and there's a very good parser already written for us. So let's just go ahead and use that. We're going to learn how to read from a standard in. It's not a requirement of the Rosalind program, but I think it's something that's very important for you to know how to make your programs do. We're going to find more ways to replace a for loop. We've already talked about list comprehensions and filter a little bit. I'm going to lean into map in this chapter to introduce that idea to you. We're going to have to talk about runtime challenges, like how much memory you're using when you're parsing very large files. Do you read an entire file into memory, or do you just try to process one record at a time? We're going to learn a little bit more about the sorted function. It does some pretty fancy things that I really appreciate. We're going to get more into formatting strings and how to use a function called sum, which will sum a list of numbers, which is handy. And we're also going to return to regular expressions to find how many times G and C occur in a pattern, in a string. So to get started, we're going to be calling our program CGC. I would like to call it gc.py, but I have a note here about how that conflicts with an internal module inside Python. So I started off calling it GC, and it caused all kinds of problems. And we've already talked about this a little bit. I said that it's possible to create variables with names like len or dict, and that's a really bad thing because it now shadows the built-in variables and functions that Python uses. So we should not use those. Your programs might still work. It might not cause a problem until after the point at which you define those variables. But it's really a bad idea. And to find them, I would suggest using tools like Pylint and Flake8. TY won't necessarily report on those kinds of problems, at least not right now. So to get started, let's just copy the first one, and I will note that if you're starting this chapter from the beginning, if you're opening a fresh terminal, the first thing you should do is source in the main directory vnv bin activate to make sure that you're in the UV virtual environment. And I can go into the 05 GC content, and I'm going to copy the first solution to the program called CGC, and I can just run PyTest real quick just to make sure that everything is working correctly. So this one is a fine example, and if we run CGC, -h, we'll see here that this bit here, it looks a little ugly, but it's because we're using the text IO wrapper here as a default, and so that's how it's represented as a string. And so we see here that what we want here now is a file. We no longer want a string or a file. We really, at the moment, we're saying that we want a file, and that's going to it's going to default to standard in. So that is basically a file handle. Standard in is a file handle that we can read. We don't want a string, so we want either something that's being piped into our program or something that just lives in a file. And I can demonstrate piping for you real quick. Like if I cat CGC, that will just spit out all of the contents of that program. If I want to cat that, and then there's, well, let me show you also another program called WC, which I can run on CGC, which will give me a lot of information about the number of characters, lines, and words in this program. WC will also count, it will also read from standard in, so I can do some things. This is very silly, but I can cat CGC into WC and it will give me the same output. Now it no longer shows the file name though, because it's reading from standard in. It doesn't actually know what the file name is. It's just this anonymous standard input. So we're going to write a program that can read from standard in, because sometimes you want to do that, especially in bioinformatics pipelines. Maybe you don't want to write to a temporary file. You just want to stream the data from one process right into your program in order to get an answer. So this is what we're going to be writing. As an example of something that we want I want you to create a file that cannot be read so that we can see what happens when our program runs with this as input. I'm going to use the command called chmod, which is change mode, to take away all the permissions, to set them to 0, 0, 0. And if I look at can't touch this, you see that there are no permissions on it, so I cannot read this file. So if I run my program that I've just copied here, CGC on can't touch this, then what we should see is a very nice statement about the error that we're getting, and it tells me specifically that permission is denied, and so that's a very good error message that I could then use to go fix my program and run it again. So that is what we're going to be programming here. And then so another example is when we run it with an input file, it's going to run with the input file and run just fine. And the other way to run this is to cat that test's input and cat it into our program. So I showed that with the WC program. If I do that with our program, you see I get the exact same answer. Another way to write that, this is actually what's called a useless use of cat. There's no point in using cat. I can use this file redirection operator in Bash and in ZSH, and I get the exact same input. So what happens here is that the operating system sees that this is the input and it's feeding this as standard in to our program. So that's a universal way that you can read from standard in. So with that, let's start over. Let's create a new CGC program with new PY, and we can run our program just to make sure it does run correctly. It says it's going to compute GC content. It looks like we're off to the races. So the thing that we need to define is a single input here called file that's going to be a text IO object. So I'm going to call it file. Whoops. Actually, I'm just going to take that one since I already have that. And I'm going to change my argument parser. I'm going to go down here. I'm going to get rid of all the ones that aren't file. And I'm going to change this. This is not going to be an optional argument. It's going to be something that is a positional argument. So I'm going to change that to file, and this is going to be how did I call it here? input sequence file. That'll be fine. Input sequence file. I like the metavar says file, and I'm changing the file type from, I'm not changing, I'm sorry, it's going to be RT, and I'm going to change the number of arguments to be a question mark. So it's question mark, if you'll recall from a chapter or two ago, I have a little table there that says it's going to be either 0 or 1. And so the reason for that is I'm going to default to sys.standardin. So the default that I have now is none, and then let's see, that covers all of the way that I'm going to define that argument. That means I need to make sure that I import sys, and with that I'm going to return args file. I'm going to go ahead and use this version, args, with setting the name of the slot, args file, and then I always like to start off with print args. Is a great way to start off. And with that, I would like to run my program. I should be able to run cgc with -h, make sure that it runs. Let me just go ahead and run PyTest to see what we've got so far. I am passing a couple of tests here. It does exist, it does create a usage, and it does blow up on bad input. But it is not doing what it's supposed to do because it's now printing this and it's supposed to be printing that. So let us go ahead and change our program to now do something useful. So when I have this file handle, I can also print args.file.name. So that is the name of the file, and if we go back to the output from this cgc with -h, remember here that a text IO wrapper has a name slot here, and so in this particular instance in the default, it's going to be set to standard in. And so if I run this with my input like tests input 1.fa, that'll be fine. I'm printing the name of that file. So that is a useful thing to know. I will say again, I know that as of when I'm recording this video in 2026, that this has been deprecated, the file type, and so technically you're not supposed to be using this, but this is the way the book was written in 2021, and I want to cover the book as it is. And this is still here. They haven't removed it from the code, so we're going to go ahead and just keep using it for now. I will probably record a video that will show you how to get around using this. What I don't like is that I have to introduce exceptions, and I don't really want to get into exception handling at this level of Python, but I think we're going to have to at some point. But since the book was written using the argparse file type, I'm just going to go ahead and continue to talk about it. So with that, we are able to pass a few tests with PyTest, and the next thing we're going to talk about is parsing the FASTA format using Biopython. So parsing FASTA using Biopython, let's take a look at this. Is what our test input. It is the exact input from the sample data set from Rosalind. So it's always a good place to start, and we have already talked about a little bit that a FASTA record starts with a greater than sign at the beginning of the line, and the sequence can be any length, and it can span multiple lines, or it may be one extremely long line with no new lines on it. There's an example in the 17 synth inputs directory. Just curious, let's go look at that real quick. Go in here, and here is an example of a real input file that I downloaded from NCBI, and we see here that there can be a lot of other information after the read ID here. This needs to be unique, a unique way of finding the sequence in the file, but after that, depending on who created this or what sequencing machine it came off of, there can be a lot of other information following that. And here we see that the sequences have been broken up. It's very common for them to be clipped to a particular length and then wrapped like this. but that really actually just introduces a lot of extra information into the file that is not really important to reading the file and analyzing it. So this actually just kind of arbitrarily inflates the file size just for the convenience of humans who often like to look at it. So it's very common for this to be one very, very long line. So there's sometimes it's called FASTA 2 format, which is that there's just 2 records per 2 lines of text per record, one for the ID and one for the sequence. So that is what FASTA files can look like. Go back into our 05 directory here. And how are we going to parse this? Well, you absolutely could read that file line by line, look for the beginning of the record, parse that out, and then read all the other lines up until the next record. And I highly recommend that you go off and write your own FASTA file. That's actually the going further suggestion for this chapter. But right now I don't want to do that. I just want to use, I want to get started. So I'm going to go into my REPL and I'm going to show you how from the bio module, Biopython, before we were importing seq, now we're going to import SeqIO. IO is for input output, and we're going to create a parser for the FASTA format using that test inputs file. And at this point, I'm actually assigning it to something called rex, because what that has created for us, if we look at this at rex records, is actually it's a FASTA iterator. And we've talked about iterators. We've created a generator, and when we created that generator, we talked a little bit about the next function. So I could actually assign the first record in rex by calling next on it. And what is rec? Well, it is this SeqIO. It's a seq record. So the SeqIO module is used for input output, is for reading sequences, and the SeqIO module will return a seq record. Inside of the seq record is a seq object. Now that is what we ended up using finally to do our reverse complement. We used the Bio.Seq, if you remember, the Bio.Seq reverse complement function out of that module to create the reverse complement. And so here we see that in the seq record, the seq slot is itself a seq object that can do things like that. It also has other slots for ID, name, description, and dbxref. So that means that I can call something like rec.id and it will tell me that. It will tell me the ID. I can also say what is the name. And they're all the same, the ID, the name, and the description. And that's because we have a very simple FASTA record that doesn't have all this other extra information, like it doesn't have dbxrefs. But the SeqIO module is designed to parse many other formats like EMBL and GenBank, which do have a lot of other information that we don't have access to here in a FASTA record. So those are just going to be set to, for instance, the sequence ID or dbxrefs is just nothing. We don't know how underneath a seq record is implemented. Is it a named tuple? Is it some sort of a dictionary-based object? We don't know, and we don't need to know. All we need to know is that there is a slot here called ID, and we can call it as rec ID, and we're going to get back this string. And that is one of the nice things about creating interfaces like this, like I've chosen to create for our args using the name tuple, so that instead of referring to it, the arguments by slot in the tuple, I'm able to refer to them by name. So we have these nice named accessors to get at this data that's in this sequence. So if I want to see, there's a couple functions that you should know about. There's a function called rep that I can use. So when I want to see some sort of if I want to print, if I print the rec, then I'm seeing a string version. And when I just evaluate the rec, I'm seeing this. When I evaluate it, I'm seeing this output, this is the output from representation of the record. And when I print it, I'm getting the string representation of the record, which I can also coerce using string. And so now you see it has these new lines in it, so I have to print it. And now I'm seeing the same output as when I print record. So it's being coerced. It's possible to take objects like this and coerce them into their string representations or this other repr output. So that's just a convenient way to see them printed out. I just point that out by way of so you understand what repr and string do. But we're going to actually access the bits that we need using the name slots. So we should be able to call, first off, help on rec, and that should show us all the things that a seq record can do. But I'm specifically pointing out here that the sequence part of it is itself a seq object. And the seq object will do a lot of things for us. Complement, reverse the complement RNA, all the things that we saw before. And so when we want to just get out the sequence itself, how do we do that? Because if we look at rec.seq, it's the seq object. Well, one thing that you can do is coerce it into a string. Sorry, didn't mean to have that star there. You can coerce it into a string and just get back the string itself. So we're going to be using that. But I also would like to point out that this is, where if I wanted, I could get the reverse complement of the string like that. And I could print the string version of that because that thing is also, it returns a seq object. So I can force that into the reverse complement. So with that, we now know a little bit about how to parse a FASTA file using SeqIO, and what we're going to get back are these seq records. So how do we iterate over the sequences? Well, we have an iterator, so we can set up a for loop. That's one way. So let me reinitialize my sequences, my recs, here in my REPL, and I can say for rec in recs, and I can, for instance, print the record.id and the first 10 parts of the sequence, the first 10 bases of the sequence. Now, when I'm doing this, it looks like a list operation, but really it's a substring operation. Remember, lists and strings in Python are kind of interchangeable. This is forcing it into the context of a string, and so it will therefore stringify the sequence record, the sequence object into a string, and then take the first 10 bases. So that's something that's good to know. Another way to coerce that into a sequence. So I can also iterate over the bases in that sequence. And so let's talk about, let's say, if I have a sequence, and let's just arbitrarily set it to this for the moment, I would like to find how many G's and C's occur in this. So I can start off, this is a pattern that we've already seen several times, I'll start off by initializing some variable to a default value. GC should be set to 0 here because we'll just assume there are none. I can say for base in sequence. If the base is in, now I'm showing this here using a tuple, but you could also use a list. It doesn't actually matter here. So the difference being here, I'm using parentheses, but I could use square brackets. But this is saying if the base is in this tuple, if it's either G or C, then I want the GC to go up by 1. And if I say what is GC now, it's 12. And what is the length of sequence? It's 19. So GC divided by the length of sequence will give me the percentage. It's about 63% GC. So that is it's pretty straightforward how to calculate GC. And so we want to go further with that. So what are some other cool things that we can do? Well, we can format this to, let's say we only want 6 places. And so I show here that when you're printing out in Python with this placeholder, after a colon, you can include some formatting information. So, for instance, I'm saying I want to print an F, which is a floating point number, and it's going to have a leading 0. It will always have a leading 0, and it's going to be truncated to 6 decimal places precision. And so this is how I could print this rounded off to a little bit shorter number. And I can also put that information inside of an F string. So here I'm giving this placeholder, and I'm calling format on the string, and this calculation will go into this placeholder and be formatted like that. I can actually put all of that code inside the curly brackets. So that code now is right here. It's the first part of this before the colon, and then after the colon is how I want to format that. And so when I run this code, I get the exact same answer. It does not matter which one you call here. There was a much older way of writing, formatting strings in Python. I think that it used some sort of placeholders. I don't remember what they looked like. This was really before my time, but you might see this % sign and then some arguments here. And I never learned that syntax. So if you see that, it's a much older version of doing this substitution into strings. I would not recommend going that way. So we now know how to calculate the GC content, and now we need to use that to find the record that has the highest GC content. And so we have a couple ways that we could go about this. We could make a list of all the sequence identifiers and their GC content, and for that I'm going to show you how to use a list of tuples, and then we can sort that list by the GC content and take the highest one. Another way we could go about this, and it's far more efficient, is to keep track of the ID and the GC content of the highest value, and then when we find a new one, just overwrite it. That turns out to be far more efficient, and I'm going to show you both because I think that there's value in looking at both of those, and I think that you'll find some really cool solutions to this. So let's look at the first one, and I would pause here to say that if you think you know how to write the solution, you should go ahead, write it, and then come back and compare notes with me. I'll show you a few different ways, and I might be able to show you something that you didn't know. The first way I'm going to write this is to use a list. Now, the first thing I'm going to do is to create a list, and I'm going to go ahead and use some type hints here. Quite a bit of type hints that I know a good friend of mine who is a Python programmer who would not like to see this kind of type information in a Python program, and that is completely fine. If you think this is overkill, it certainly is. I'm just trying to show you how you could use some tools to write code that might be easier to maintain, especially as your programs get quite a bit larger. So for this, I'm saying that sequences is going to be a list, and each member of that list is going to be a tuple, and the tuples should have the structure of being first, in the first slot there should be a floating point number, and then in the second slot there should be a string. And for this I need to import both list and tuple from the typing module. So I'll do that. It does not matter what order you put these in. We have instantiated, we have defined this as an empty list, and now we don't, one of the nice things here is that we don't need to open that file. The argparse file type already has done that, so SeqIO wants to have an open file handle, and that's very handy. So I already have an iterator. I don't have to write any code to parse this as a FASTA file. And if you read SeqIO parse, you'll see all the other formats that it will parse, like FASTQ, which has quality information. I believe it will do GenBake and MBOL formats. So it's extremely handy, and we don't need to worry about all the intricacies of parsing these different formats. We're just using SeqIO. And I'm going to take this exact same code that we had here that I wrote. Let me just see if I can just copy this. I'll go over here, paste this in, and then I'll have to indent it. So for each one, for base, if the base is in GC, then we're going to increase our GC content by 1. Go back here. And so for each record, I'm computing the GC, and I'm going to say the percent is going to be the number. So the percent is going to be whatever is the GC content times 100 divided by the length of the record, and then I'm going to append to my sequences a tuple that contains the percentage and the record ID. And that's pretty cool. Let's just print seqs and see what we have here. And I like to run it. Let me get out of here. I'm going to run my CGC program using tests inputs 1.fa, and SeqIO is not defined. I forgot to bring that in. So I just need to jump up here and from bio import SeqIO. Very important. Let's try that again. And let's see. I need to change this to rec.seq. I may even have to stringify it. There we go. So what I have here, and let me go back and bring in pprint from pprint import pprint. This could really make your life a lot easier when you're trying to look at the output from your program. It can be very difficult to look at these long lines, and so I have decided to use pprint to print this as a structure here that's a little easier on my eyes to see. And now I can quickly see this is a list, and each member of the list is a tuple, and the tuple has a floating point number, which is the %GC, and then the record ID. It's exactly what I want. So with that, I now have at least all of the information that I need to find the one with the highest GC content. So I'd like to point out some things about the way that Python sorts lists, which is really quite nice. So here I'm showing if I have a list of strings and I call sorted on them, so this will return a new list with the items put into some sort of order. If the inputs are strings, then it's going to sort them what's called lexicographically, meaning just kind of alphabetical. Keeping in mind that uppercase and lowercase values are sorted differently. So this is a case-sensitive sorting. And that's important to know. If you want a case-insensitive sorting, then you have to do a little bit of extra work. If you call sorted on a list of numbers, however, the numbers are sorted numerically, and that's really nice. If you put the numbers as strings, then you're going to get a very different order, 1, 10, and 2, because the 1 here as a string sorts before the string 2. So it's very important that if you want numerical sorting, that the values actually be numbers and not strings that look like numbers. And I have a little sidebar here about, in my very humble opinion, lists should be homogeneous. And there are several languages that enforce this. For instance, in C and in Rust, you cannot mix strings and numbers. And there's very good reasons for this. It has to do with the way that these data structures are laid out in memory. And Python treats lists very differently from those two languages, and you're allowed to put whatever you want into a list. And what happens is that if you call sorted on 2 and then the string 10 and then the number 1, Python's going to try to compare these two, 2 and 10, to see which one goes first, and it doesn't work because it cannot do a comparison between a string and an integer. And I have this that it's acceptable, but it's like this joke by Henny Youngman. A man goes to see his doctor. He says, "Doc, it hurts when I do this." And the doctor says, "Then don't do that." And so that's essentially what we have in Python is, yeah, this is bad. It's going to break your code, so don't do that. And there's nothing in Python that will stop you from doing that. And this is exactly why you might see someone like me go to the effort of putting type information that says this list is going to be everything in this list is going to look like a tuple with a float and a string. And then I'm not allowed to go stick in just a string. I mean, I can. Python's going to allow me to do that because Python simply ignores the type hints. But a tool like when I wrote this book, MyPy was pretty good. MyPy at the time was able to see, hey, you're appending a list. You're appending the wrong type. You're appending a string, but what's expected is a tuple with a float and a string. So that's useful. That's something that I can learn about my program without running it and waiting for it to fall over. There are other ways. There's at least one way in Python to enforce that something like a list has everything that is of the same type, and one of those things is to use NumPy. So this is for doing numerical processing in Python, and it's quite powerful. One of the reasons why it's so powerful and fast is because underneath it's implemented in C, and C has this requirement that lists be homogeneous. And so if I try to create an NP, they call them arrays, not lists. So if I create an array with a 2 and then the number and then the string 10 and then a number 1, it's actually going to coerce everything to strings, because it says I can't mix these types, and you have a string in there, so now they're all going to be strings, which is not great. You should actually make sure that your data is all going in as numbers, right? If they're supposed to be numbers, so you would need to fix this. It is possible to take a list like that, 2, 10, and convert each one of them to a number, and we can do this using a list comprehension. For in this list, return the integer value of n, which that works fine. That is a way of turning that original list into a list of numbers. And I'd like to take that just a little farther, because I'm going to be introducing map here. Map takes, it's another higher order function. We talked a little bit in the last chapter about filter. And so map, like filter, takes as its first argument some anonymous function. Often it will be written with a lambda, which I was writing it before, but sometimes I assign the lambda to a value like f. So I was just passing what looked like something like this, like the name of a function. Here I'm passing the name of the function int, which I just used here. I'm saying int takes a single argument, so I can just pass int, and int is going to be applied to 2, 10, and 1, and that is a lazy function. So if I were to take that and run it in the REPL, it's going to give me a map object, which I can then coerce into a list as 2, 10, and 1. And then therefore another way I could coerce that is to call sorted on it. And now I get 1, 2, and 10 sorted numerically, not like strings. So this is a little sidebar. You're going to be seeing some of these ideas here coming up. But a map is a way of applying a function to every member of some sort of an iterable. Now, with that, consider what happens when we try to sort our list that has this content of tuples. So I'm going to call it Rex here, and I'm going to assign it that value. And if I look at Rex, we see here that they're in this particular sorting. So if I say sorted on Rex, what happens is that let's see, are they in a different order? Yes, 53 now comes second, and this 57 comes first, and the 60 comes last. And so what happened here is that Python first sorted the whole list by the first element in the list, and then it sorts by the second element. So here you see 01 and 01 have the same value, and I specifically put bar after baz so that when these are sorted, here you see bar comes before baz. And so that is extremely helpful. So that's what's going on here. It's what's going on here. If I have a list of tuples and I made sure to put the score first and then the ID second, it's going to sort by the score first, and then I can take just the last one, which has the highest value. I can take that and then look at the ID. So it would look like something like the last one dot ID. Let's see, sorry, dot one. We haven't gotten to that, but that is the ID of the last tuple in this sorted list. I can also here I'm showing. Oh, I'm calling it seeks here. I need to change that. I called it rex. So I can say which one is the high. It's that one. And now what I need to print out, excuse me, is the high one, but I want to print out the first bit, the one what's in the slot 1 is the ID. I want to print that. It's followed by the score, which is in the 0 slot, formatted to six decimal places. So let's take these ideas and finish off our program and make sure that we have something that is working. So if I want, I can now take the highest. Let's see, and I'll just take that from the text here. So if I sort the sequences, I can get the high value. And then what I want to do is print the highest one. I want to print the ID and the score there. And let's go run it, CGC. We'll run it on tests inputs 1. And I should see that. I believe that is the right answer. Let's run pytest.xv. And we see this is the version that passes. And so if you're satisfied with this, you can move on. But I'm going to show you a few more tricks. The idea here is we are trying to learn as much as we can about Python here to see how it can be useful to us in the future in writing programs. So the first thing I'm going to show you is how to add some type annotations in unit tests. So inside of this for loop is a bit of this whole thing right here is calculating GC content. That's something that we could write a test for, and we could be therefore sure that we're getting it right, or have some more assurance that we're getting it right. And so I would say that a good way to start off writing this is to write the function definition and just to start off returning 0. And so we're going to write a function called findGC, and it's going to take as its input a string, and it's going to return a float. And whether or not you like the type hints, you have to be you have to admit that it does provide a level of documentation for the reader of the code. So now it's very easy for me to see what this takes and what it returns. Without a return value here, I would just have to read the code. And in addition to that, there's nothing stopping me from returning an empty string, some sort of a string value. And then I've now broken this contract because I've said that I'm returning a float, but I'm actually returning a string. And sometimes you have a decision tree, a bunch of if-else's, and under one condition you return one item, something, a string, and under another condition you return a float. Well, that's going to be a problem. It's probably going to break some code. You really need to return one data type and learn how to deal with that. And so if I were to write code like this, especially if this were in some sort of a big nested loop or some big decision tree, and I didn't realize that I was returning a string when I said I was returning a float, well then some tools might be able, let's just see what TY says. Let's TY check our CGC program. I've said that, yep, I've said I'm returning a float, and it sees that I'm returning a string. And so that is the kind of information that I would not get if I didn't have this, right? If I don't have the type information, then it's fine. I can return whatever I want. I could return a string if, the day of the week is Monday. If true, else I'll return 1.0. And with that, let's see, I wonder what TY is going to say. Yep, it doesn't matter. So under one condition, I return a string. Under another condition, I return a float. And honestly, that's terrible. That's really a bad way to write code. But it passes all the checks, and Python doesn't have a problem with that. I'm just telling you, it will lead to tears. So here I'm starting off by returning 0 point, which is a shorthand way of writing 0.0, which is a float. Just because I said this is returning a float, And if I were to return 0, that I'm returning the integer 0 here. It's not going to be coerced into a floating point number for me. And interestingly, ty doesn't see a problem with that. I wonder if I put 1 there. Interesting. That's definitely not a floating point value. It is an integer 0. So I want to return the floating 0 right now. And because we're talking a little bit about test-driven development, I'm going to show you how to write a unit test for this. So I'm going to go ahead and actually, let's see, I'm going to copy this from, let's see, solution unit. Let me just go over to solution unit and copy this test so that I get the formatting correctly. And what's important about the order of operations here is I'm now going to run PyTest on my CGC, and I know it's going to fail. And this is generally how test-driven development is intended to work. Is that I have stubbed out this function that with the bare minimum of code to make it exist so that I have something to test. And I'm saying it's going to accept a string and return a float, and right now I'm just not doing anything. I'm just returning a 0 under all conditions. And I'm writing a function called test find GC. It needs to start with test underscore, or I believe it can end with underscore test, but I like to put the test at the beginning so that it stands out to me, but this is also for PyTest to be able to find. What you put after that is up to you. I like to just put the name of the function after it. And in fact, I like to put it exactly after the function that it's testing so that it provides yet another piece of documentation for me so I can easily see when I pass it the empty string, I should get back 0. Again, that's a design decision that you may decide that if you were trying to find the GC content of an empty string, that should be some sort of an exception. Maybe your program should halt processing, but I'm writing this test to say that if given an empty string, it's going to return 0. When you're writing a function like this that accepts, a string, I always test it with an empty string. I don't feel the need to test it with something like a none value or an integer because my hope is that by using type hints, I'm not going to get to the place where I'm accidentally executing my function with the wrong type of input. I'm hoping that if I say this takes a string, that I'm not going to go through all the effort to test all the different, is this thing a string? If it's not a string, then I'm going to throw an exception. I don't tend to write Python code like that. Again, I tend to code the happy path. So assuming that I get a string, I'm just going to assume at this point that it is a string, and I'm using type hints to ensure that I actually get a string. So given an empty string, I know that I'm going to return 0. Given a single string of a C, that there's 100% GC content, same for a single string of a G. And then given some other known strings, this is 100%. It's a only C's and G's. This has no C's and G's. This has 50% C's and G's. Given that, I now have a test that I know is failing because it's always returning 0. And so what I can do now is, even though this is going to break my program, I can move this here and I can return. Now this part of the code is broken because there is no %, and if I were to try to run ty check on ty check on my CGC program, all kind of things are going to be broken. But it does not change the fact that I can still run PyTest on this, and it's going to execute just the test code. Oh, actually, okay, so I called it seek here and rec seek here, so I need to fix that. So we run this, and rec, again, we don't have rec because we have a sequence on, we have just a string sequence. And now illegal division by 0. Interesting. So this is why we write tests, right? So that we can make these assumptions here that it's going to work, and it doesn't, and that's why we're writing tests. So let's go find about how we can write this. So we need to put a condition there. If there's not a sequence, we want to return 0. So that is a way of ensuring that we don't divide by 0. So what does it mean not seek? So let's just go back to the REPL real quick, and let's say seek is equal to the none type. And I could say if seek, I'll say print, I'll just say okay, if seek, else bad. And what's happening is that seek is being evaluated in a Boolean context. So it's not false. So it would make sense if seek were equal to false. This line would make more sense. But if it's equal to none, then if we say what is the Boolean value of seek, well, it is false. If I set seek equal to the empty string, what is the Boolean value of that? It's false. If it's anything other than the empty string, even if it's a string with a space in it, then it's now true. So I'm just saying if sequence is none, if it's the empty string, if it's anything that evaluates in a Boolean context to false, then we're just going to return 0. Otherwise, we're going to go forward with this code, and we now should have something that does not blow up. And this is exactly why we write tests for this, because we didn't think about that when we created this function. What happens if we get the empty string? Well, we're then get into divide by 0 territory, and that creates a bug, and that blows our program up. So now we have a function that works pretty reliably well, and that we think is not going to break our code. And so just going over this. This is test-driven development. You define a function that you want to test, you write the test, and then you run that test to ensure that the function fails. It should fail. Then you make the function work, and then you ensure the function passes the test. And all of the other tests that you've written up to this point as well. You may inadvertently break something that used to work when you added this and you refactored your code. So, and I have note here that because of the type annotations, I don't really worry about a bunch of other esoteric bugs, and I just try to keep it simple. Everything's a balance in life, and I'm trying to add just enough type hints and just enough testing to make my programs work, but I'm trying not to create too much of a headache for myself. So, moving forward, I want to make another addition to this solution. I want to create a custom type. We've already done this, in every program using the args. And I want to do the same thing, but I want to create something to represent that tuple. So it is a tuple. I've been using a tuple up to this point to represent that. So I like to put all my class definitions up at the top. And I'm going to create one called mySeq, and because I could call it seek, but then it could start interfering with the Bio.Seq, and I'm going to call it mySeq. I could have come up with something more interesting, but it has 2 slots, just like all tuples do, and I'm saying that the first slot is float and the second slot is a string, and furthermore, I would like to be able to refer to them by GC and name. So now I don't have to remember which one's in the first slot and which one's in the second slot. And so with that, I will it changes my code a little bit. Now my type definition changes. It actually gets quite a bit tighter now. I really appreciate this. Now this is going to be a list of mySeq. That, to me, is far easier to read than the previous definition. And it just kind of rolls off the tongue. And so instead of appending a tuple, I'm going to append a new mySeq object. So it did look like this, where I was manually computing the GC content, and now I'm going to get back. I'm going to call find GC on that sequence record, and then I'm going to use the record ID to create a mySeq object. And so my code now looks like this. So let's print seeks and see what that looks like. And nothing else needs to change. All the rest of this still works. sorted on seeks is still going to work because my seek is still a tuple. It still has the score, the GC content in the first slot. And so that should all still work. Let me just verify this. Let me just run PyTest on everything. Yes, it still works. Let's actually run it so that I can see that output. Test. Oh, did I print it? Yes, print seeks. Whoops, didn't mean to do that. So I'm running CGC on test inputs 1. Oh, let's see, I wanted to see, there we go. We see here that when we print this, that it is printing them. It is stringifying the mySeq. I didn't have to add any of that to this. Let me run it like this. It seems to be working. Let me run PyTest -v. Passes all my tests. So this is another working solution that we can use. And not much changed except for I added some type annotation. I added this new type and so that it changes, I think it makes my code read a little more clearly. And now I also have this, if I run make test now, then it actually, let's see, it is unhappy because I've imported pprint and I'm not using it. So that was actually an error from Flake8. So Flake8 didn't like that, and now it's unhappy that I'm importing tuple and I'm not using it, so that's fine. I'll be happy to do that. So when I run make test, it's running all of the tests that I've written and in addition running Flake8. And so I see now that my program is pretty good. I can run ty check on this. It doesn't see any problems there. I've got a test I've got an integration test for the whole program that I've written there, but I've also got a unit test for this one particular function that I wrote, and in the course of writing it, I realized that I was dividing by 0, so I fixed that. So that is moving towards a better solution for some values of better. So what can we do else? What else can we do with this? Well, one of the problems that we have is that we are keeping track of all of the data in our input file, and we really only need to keep track of one. Everything in bioinformatics is about scaling, and so you have to think, what's this going to be like when I use 1 million sequences, or 1 billion, or 100 billion? You just have to imagine that you're going to get inputs that far exceed what you're using in testing. And so here's a solution where I'm going to create a high that is going to be a mySeq for element. So instead of keeping track of a list of mySeq, I'm just going to keep track of one. It's going to be a mySeq object with a GC of 0 and no ID. I could have gone about this some other way, but I just decided to create this dummy record. And now I'm going to find the GC content. So let's get rid of that. I'm going to find the GC content of this sequence record. And if the GC content is higher than the current high one, and I'm able to compare gc.high.gc because this is a nice named tuple. If the percentage that we just found is greater than what is currently in the high slot, then the high slot is now going to be equal to a new mySequence object with this percentage GC and this record ID. And now I can also replace the way I'm printing this out. Instead of calling high like that, I can call, first off, I don't need to figure out which one is the high. I've already figured it out, and I can call high.name and high.gc and format it like this. And so that's pretty swell. Let's give it a try. Does it pass the tests? Yes, it does. Just always nice to run it with input and see the output. Yes, that also passes our test. And it's hard to see with such a small input, but this uses significantly less memory. And so, I would challenge you to go find very, very large data sets to test this on, and try the different ones and see what the run times are like. And so for this solution here, I could write the GC, the find GC, just slightly differently. So let's talk about this. This is another way of writing find GC. Let's see. So replacing all of this with this version. First off, let's run pytest -v on CGC, so it's only going to run just the test GC. So this version also passes the test that we wrote. What I'm doing here, and let me pull up a window here. I'm going to assign seek equal to AACCGGTT. So should be 50%. If I say seek upper, first off, if I had, let's say, those G's there, seek upper is going to now take into account the fact that I could have soft masked DNA here. So this is another way to think about this. If I wanted to ensure that I was handling soft masked input, I could change some of these to be a lowercase and make sure that I'm getting the right answer. So I'm going to force it to uppercase, and then I'm going to call count, which we saw before in the very first chapter when we were counting nucleotide frequency, that I can use count. So I can count the number of C's and I can count the number of G's. And so I see 2 and 2. That's what I'm doing here. So if I add those two together, C plus the count of G, that's 4. If I multiply that times 100 and then divide by the length of the sequence, so I can get, so if I add those two together and then multiply by 100 and then divide by the length of the sequence, I get 50%. And I have this all couched in an if expression. So here at the end, and I don't love this syntax about Python, but it's fine. So it's going to execute all of this if seek, else it's going to return 0. So it replaces a lot of lines of code with one very tight if expression, and uses count here to count the C's and G's, and uses upper to force it to uppercase. And so if I run this, I can see that it passes here. I've now put into there some lowercase variables, some lowercase input, and I ensure that it seems to work. I could mix this here like that, ensure that it still works. And now when I run my pytest -xv, I see I'm passing all my tests. I can run make test. Let's see if it is not happy because I've imported typing list and I'm no longer using that. So flake 8 was not happy, so let me go back and run make test. Let's see, it does not like the continuation of a line underindented on line 65. So it does not like the way I wrote this. Let's see if it likes that. And now it doesn't like that the line is too long. Let's see if I will, okay, so I just ran it through a formatter called black, and black formatted it like this, and still we're having, so flake 8 is not happy with it. So we're just not going to worry about it. We can't make all the people happy all the time, and so that's fine. It does pass all of our tests, all of our unit tests, and so we will just go with that. I'm going to go back to the way I wrote it like that. I think that's fine. Just curious, I'm going to try one last thing. I'm going to put a line continuation there, and let's see if it likes that. No, it does not. So that's fine. I'm happy with that solution. So with that, we have found a different way to run this. So now I want to talk just a little bit about benchmarking, and to do that, I wrote a program here called Youens-Clark. So I recommended, you go find some big sequence input. You don't have to, because I wrote this nice little program for you. It will generate some long sequence for you. It has an average sequence length of 500, and the number of sequences will default to 1000. And there's some other parameters here that you can use, and it's going to output this file called seqs.fa. So if I just run this genseq, it's going to write 1,000 sequences to seqs.fa. Let's look at what seqs.fa looks like. They're just arbitrary FASTA sequences with a bunch of just arbitrary names and DNA sequences of just random mixes of C's, A's, T's, and G's. And so now if we run our CGC on seqs.fa, then we see it takes just slightly longer. We could run genseqs, and let's change the number to 1 million. And that's going to take a second to run, but then it will give us something more like what you might see off a sequencer. Very, very common to see millions of sequences coming off a sequencer, and so you want to analyze those to see how much GC content there is. You can really get an idea of how much more slowly the version runs that uses that puts all of that into memory. I don't actually feel like waiting for this to finish. This is actually taking quite a bit of time, so I'm going to get rid of that. But that is a way of creating. So here I have, I suggest that you could create pretty easily 10,000 and put it into a file called 10,000K. And if I look at 10K, it's actually going to be 20,000 because there's 2 lines per FASTA sequence. And so 20,000 lines of input. Let's see how heavy that is. $-LH on 10K, and we see that it's 5 meg, which is a very, very small FASTA file for what we typically process in bioinformatics. So I have here an example of how we can use Hyperfine to test these two solutions, see how they compare to each other. There's a typo here. The solution to is not called unit test, it's just called .unit.py. So if I correct that and I try to run this on the command line, on my laptop, I'm going to get an error. And I want to step through this with you because it's a learning opportunity. So I run Hyperfine and it's not working. But it does say that I can use show output to figure out what the problem is. So when I do that, I'm going to see something that was very surprising to me when I was started to record these videos. It says that I'm missing a dependency for NumPy. And that's frustrating because if I look at the requirements file, NumPy is certainly in here, and I know it's been installed, and I spent several minutes working through this solution to figure out what the problem was. And it turns out it's a problem because I'm using a MacBook Pro that has an ARM64 processor, and the NumPy installation that gets installed on my system is broken. It just doesn't work. You probably won't have that problem if you're on a MacBook that has the Intel processor. And there is another machine that I have access to. I'm lucky enough. I have access to a Linux server through my work with the University of Arizona. And so if I go set up my environment over there and I run this, and let me expand my window here, so we can see the proper way that I'm running this Hyperfine. I'm comparing solution 2 with solution 3, and I'm comparing it on that 10K file that I ran, that I created with the genseq algorithm, the genseq program there. We see it looks like the maxvar ran about 1.76, almost 2 times faster than the other one. And that's just on a solution, that's just on an input with 10,000 sequences. Imagine how much faster it would be if you run it on a much, much bigger input. So that is one thing that you can do to try to figure out when you're writing solutions is to create 2 different programs and benchmark them with something like Hyperfine. So another way to create a list, to use a list comprehension, it includes something called a guard. So what we see here is that I could write a for loop for base in rec seek upper, and here I'm now going back to considering the fact that I could have upper and lowercase input, and I could say if the base is in CG. So this is another way of writing essentially list membership. If this string is in this this other string, this is actually a way of looking at substrings. So let me just demonstrate that real quick. So given a string like, seek is equal to AACCGGTT, I can say C in seek, and that says true, but I can also say CCG in seek, and that's also true. So it's actually doing a substring. Can I find this substring in that sequence? So if I were to add, for instance, CGT, that is not in that particular substring is not in that sequence. So we see the same thing here, like if we say C in, if I were to, let's go back to making this into a list. How about this? If this were a list, then it looks like this. And now if I do these comparisons, they're very different. So is C in seek? Yes, it is. But now this CCG is not in seek because it's looking for the string CCG that's in the a list of characters, and there is not a string in this called CCG. So you're going to get very different answers depending on how you're doing these comparisons. But if base is a single base and I'm looking at it in this string, this is going to work. So what I'm saying here in this list comprehension with a guard is for the base in each in the sequence, return the base if the base is in GC. So this is a way of very quickly creating just the bases that are C's and G's, of filtering them out. So I'm just showing you yet another way of finding all the C's and G's that are in a string. So we've already seen going through manually with a for loop and doing our comparisons, and then we saw using string count, which we had used from chapter 1, and now I'm showing you how to write a for loop, a list comprehension with the for loop inside of it and a guard on the end to only return those. And so with that, if I know the bases that are C's and G's, now I can just count them. And so if I want to incorporate this into my find GC function, I'm going to write it like this now. So let me go back to my CGC program, jump down to my find GC, and another way to write this is if there's not a sequence, just return 0. Otherwise, force this to uppercase, only find the ones that are C's and G's, and take the length of that, and then return the GC times 100 divided by the length. That should work. Let's assure ourselves of that. PyTest-xv, and I'll just run it on the CGC program so that it will run just the unit test. That works just fine. And now if I run it on the test suite, that runs fine too. So yet another way of finding GC content, and now you have seen a list comprehension with a guard. That I introduced. It is in and of itself an extremely useful thing to do, but I introduce it in that order to now show you another way to write the same idea using the filter function, which we saw in the previous chapter. So this is exactly the same thing. Let me go back into my REPL, and if I take that string and I run it through a filter, the filter wants as its first argument a lambda expression or some sort of a function that takes the input and returns a Boolean value as to whether or not this thing passes the filter. So for each base in this string, base is going to be passed into the lambda as base, and then I'm saying is base in CG, and only the elements that that are true, for which that is true, will be returned. So you see A and T, they do exist here, but they were not returned by the filter. And without, you're probably already familiar with this, but without the list, I just get back a filter object, which is, this generator that will be produced when I actually need the value. So I'm calling list here to force that evaluation. So another way of writing this idea is to find GC. Let's see, I have to make sure. I'm replacing this line. I'm forcing the sequence to upper, and then I'm running it through a filter. Each base in seq upper is going to be compared to, is it in CG? And then that's going to give me the length. And I take the length of that list, and that will give me GC. Just a note real quick that if I can't just take length of filter. Filter needs to be coerced. That's why I have the length of the list of filter. I have to coerce it here in my code, otherwise it's going to break. So with that, I have exactly the same way of writing. This is basically the guard condition here. The guard is what is happening in the lambda. And now it comes first because it is the argument to filter, and then the thing that I'm iterating over comes second. So now you have another example of using a filter function. So filter is a higher order function. Higher order functions take other functions as arguments. And so I want to show you map, which is perhaps one of my favorite functions of all time. And it also takes as its first argument a lambda function, some bit of code that will be executed for each element in an iterable. So for instance, let's take this as our input sequence. And I'm going to create a list of ones and zeros. Whoops. I want to create a list of ones and zeros. If I'm going to return, this is an if expression. If base is in CG, I want 1, else I want 0. And so now I have a list of ones and zeros, which correspond to the places where C's and G's occurs. And now I can do something kind of fun. I can replace the list with a sum. And sum will coerce the map. So without this, just again to prove this to you, without any coercion, map just returns a map object. So sum will actually consume the map object. It will go through the ones and zeros, and it will count up that there are 12 ones. That is the length of the GC. And so something that I want to point out here, if you take, like, I think it's in math and computer science, I think it's called like discrete math or discrete functions, something like that. I sat in on one class and I got to the truth table. So when you have true and false, you have 4 different options. You have true, 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 false, false, true, false, false. And so, how do those evaluate together? So true and true. If you have 2 true values, then that's true. If you have true and false, then that's false. If you have false and false, then that's false. And it doesn't matter if false comes first. If you have false and true, then, well, that's false. So that's your truth table for just true and false. And so that's really useful to know. And of course, you can do it with or as well. So if you have true or false, then it's true because one of those values is true and it doesn't matter what order they're in. So all of that's very, very useful. What happens if you do true and you were to happen to use plus instead of and? Because, you just weren't thinking. What is the output of that? Well, would you be surprised to know that it's 2? And so why is that 2? Why is that not actually some sort of an explosion? Why is that not an exception? Well, what happens if I do true plus false? That's 1. What is false plus false? It's 0. Well, perhaps you can see the payoff here. Underneath, these are just integer values. So if I say true is equal to 1, that's true. and false is equal to 0. That's true. So there's actually a secret life here. Python Booleans are underneath, they're just integer values. So that actually means that I could, instead of returning 1 and 0, I can simply return, let's look at what this looks like. I could return whether or not the base is in CG. I'm turning seek into a list of bases, and I'm saying the base is in CG. That's actually going to return true and false. And so if I therefore sum that list, I get 12. So that is another fairly short way of writing the same idea. I can replace this, and as you can imagine, PyTest. Let me run make test. Make test, so I can run all of my tests. That runs, because that's going to run it on both CGC and on the test that I've written. I see that is another way of writing that. And what you learned along the way is that there's a dirty secret here about Booleans or integers, and that you can actually just sum them up. So that's kind of crazy. Okay, for this next solution, I want to go back to using regular expressions because they are incredibly useful, especially in genomics when you're looking for patterns of text. It's definitely overkill in this instance here, but you're starting to get a flavor here for why they could be useful. What I'm going to do, I'm going to go back into my REPL, I'm going to import RE, and I'm going to run this bit of code. RE find all is a function that is in the regular expression module, and I'm passing it here something that we have not seen before. This is a pattern that uses a character class. So a character class is created by using square brackets, and inside the square brackets are the alternations that you want. So you're saying find either G or C in this string, and when I run that, it finds all the C's or G's in this string. And so you've seen that data structure. All I need to do is now call len on that. The length of that is 12. So another way to write this is GC is going to be equal to the length of that, and in order to use that, I need to jump up here and import RE. So I don't believe there's anything else I need. Let me just double check here. There is, I do still need, okay, let me just, I'm still checking here if the sequence is equal to 0 and if there's nothing in the sequence. The way I've written this here is using an if expression. So let me go change this real quick, because what I'm showing here is one line of code. Pretty slick line of code. Let me run make test, and it is not happy about that. Let's find out. Good learning example here. Well, maybe I have just a. Let's just see if it compiles. And I'm going to pause for a second. So sorry, I didn't read ahead here. It's very crucial in this solution that I force this to a string. So this will work just fine if I go up here and force this to a string. And now I believe everything will. And so, well, let me just point out the error that I was seeing when I ran this. It says expected a string or bytes-like object, and it got a seek. It was not happy with this line here, the return length find all. And so the reason was because I wasn't actually passing a string. Let me make that into a string, and then I will make test and verify that it all works, and that is another way to write this. So I just needed to read my own error message. So another more complex And so why are we making it more complex? Well, sometimes your code needs to have a bit of complexity in order to handle very complex problems that we encounter in the world. And so here I want to change my find GC so that it accepts a seek record object. So before in fact this blew up because I was passing it a seek record and it really just wanted a string. And so I want to write it so that I can actually just pass it straight in what comes out of SeqIO. I want to pass it a SeqIO, a seek record. So I'm going to change my find GC. The first thing here is I'm going to change this to accept seek records. And I believe I'm going to have to, I'll probably have to import that, a seek record object from Bio.SeqIO. But I'm not going to worry about that at the moment. Here I'm showing in the REPL that I can create a seek record object just by importing these records, these types from Biopython. So and that's going to be important because I'm going to change my this to be now, instead of a string, it's going to be a record. So it's still going to return. No, actually, it's not going to return a float. Now it's actually going to return a mySeq object. So it's changing quite a bit. We're still going to calculate the GC content, but we're going to return the GC content and the record ID for a sequence. So we're changing this function quite a bit, and it still has this core bit of code to it. And I'm going to have to paste it and then fix the indentation here. So the percent is going to start off equal to 0, and if we're able to get a sequence out of that, if we're able to coerce this record, the record seek, and we stringify that, and if it's possible that when we assign this to seek, that seek is something that evaluates to true, then we're going to calculate the GC content by using our re-find-all, and we're going to calculate the percent by doing the division, and then we're going to return a mySeq object that's going to have the percentage that defaults to 0, and then the record's ID. And this brings up something called the walrus operator, which again, a lot of Python people do not like. So this combines actually two operations. In the old way of writing this, you would first assign seek to be that, and then you would say, whoops. So I would assign it, and then I would say if seek, then do this. And so evaluate this expression in a Boolean context and then continue forward. I was actually really happy when Python added this in PEP 572. And so I come from the language I used most before Python was Perl, and we did this kind of thing a lot in Perl. And so you can blame that on me. If you don't like the way I've written this, then you're welcome to write it the more old-fashioned way. So if it's possible to get a sequence and assign it to this, and it's something that looks truthy, then I'm going to calculate the GC using that, and then in any event, I'm always going to return a mySeq object with some sort of percentage there, which could be 0, and whatever is the record ID. And that is going to very much change the way that I write my code, but I should be able to now run my test. I want to just see, am I able to run this? I'm sure it's going to fail here because I need to import, I think I need to import a couple more things. Yes. Let me just go look real quick at this is the solution, let's see, I think we're on solution 8 here. And I see here that I've imported a couple more things from Bio. I need those, and I think that's probably all I need. Let's give it a try. Let me just, to make it easy, I'm going to copy the solution 8 to CGC, because that is what I was building up to anyway. Let's just run PyTest on that. and that works. And let's see what our version of the program looks like now. So I've got all the imports that I need, and I have now, I'm creating a sequence record object with a empty sequence and some ID, and I see here that it's going to return 0, 1, 2, 3. That's great. Here's an instance with 1C, 1G, 100%. Here's with 50%, and here's with 100% as well. And so I've got, you know, some tests that seem to cover some basic spectrum of what I might see on my input. My find GC now takes a sequence record and always returns a sequence object. And that changes the way I write my for loop now. So now the for loop can incorporate a map function that will turn each sequence record into a mySeq record. So check this out. So for sequence, I'm saying map into my findGC function. FindGC expects a sequence record, and it's going to return a sequence object. So each one of these sequence records that's returned by SeqIO parse is going to go into findGC, and that is going to return a mySeq. And now I can say if the sequence GC is higher than the high GC, then my high is now equal to that sequence. And I just print at the end the same high name and high GC. And that works as well. That is another way to write this idea. And it incorporates, crucially here, it incorporates a map to turn one thing into another thing. It turns a record, a seq record, into a mySeq that has the GC calculated. So that is something else that we can do. Finally, we need to figure out which one at least is the fastest. It may or may not be the best solution. And when I wrote this book a few years ago, and I did benchmarked all of the programs against each other in the directory here, the 05 directory, there is a bench sh file that will run this. And solution 3 came up as the fastest. And at the time, it was running it just on that Seq's FA. And when I ran it this time, running it on the Linux server that I have access to, there was barely any difference at all between the programs. So I decided to modify the program and instead to run it on the 10,000 because I was able to see a little more, a difference between 2 and 3 on that. And so when I ran this on all of the solutions that I have, solution 3 is still coming up as the fastest one, up to perhaps 3 times faster than the version that uses regular expressions, which again is not that surprising because the regular expression searches are more expensive than some of the other things that we're doing. But it is very worthwhile knowing about regular expressions because sometimes you may find that it's the only solution available to you. So I feel like we learned a lot of really cool things along the way. We're able to explore some interesting ideas, but when it comes down to it, if the thing that we have to do is churn through a lot of data very fast, it looks like this pretty simple solution that we wrote that uses a tuple and just takes care of tracking the maximum version, that looks like that's going to be the fastest program that we can run. So going further, I do encourage you to write your own FASTA parser. And to do that, I would encourage you to make a directory and go in there and start off a new FASTA parser. And there is an option there where you can actually have it create some tests for you. New.py can do that. And so it gets you started. And I would encourage you to put in some input, put in some FASTA input, put in some input that's not FASTA, and try to figure out how would you go about writing a FASTA parser, and how would you have it deal with badly formatted data. There's a lot that you will learn by writing that, and you will see why it's so useful to use other people's code. So a lot of considerations for how you would want to write this, and I just encourage you to have fun with that. So some of the things that we learned in this chapter, one of the things was reading from standard in. We didn't cover that really in the way that we ran the program, but let's just run our CG program. If we pass it, for instance, the 10K file, it does work, but we could also pass it like this, where it's reading it from standard input, and it's also giving us the same answer. I can also cat the 10K and pipe it into CGC, CGC.py, and it still gives me the same answer. So however I choose to run this program, whether I pass it the file name or I pass it as standard in, it works. And that was simply because we use sys.standardin as the default input. So you now know how to read from standard in. You've now used the Bio.SeqIO parse function to parse FASTA formatted sequence files, but you can also use this to read FASTQ and other types. We used several ways to visit all the elements in an iterable, from for loops, list comprehensions, list comprehension with a guard, filter, and map. We saw that a list comprehension with a guard is just another way of writing a filter, and it's up to you which one you find more readable, but either of those is, to me, preferable to initializing a value before a for loop and then altering the value in the for loop. We talked about writing an algorithm to avoid storing all the data that was in the input file, and because that could actually eventually exceed the available memory on your machine. We talked about the sorted function and how it how it blows up if the input list is not homogeneous. So if like you're mixing strings and other values in there, it's going to blow up. But the other thing about sorted is that if you pass in tuples, it will sort by the first elements of tuples and then the second elements of tuples, and that is very, very useful. We talked about formatting templates with and how they're like printf, and we use the formatting template to round off to 6 places on a decimal number. We used the sum function to add up a list of numbers. We talked about the fact that Booleans are actually integers, and so we can actually sum the Booleans. And we used a regular expression to find patterns of text. We used a character class to look for C or G. So quite a bit of things that we learned in this chapter. I hope you found that useful.